Okay, team, so I'm back again with a little video here. This is a continuation of our video series from problem set 1 from the energy review unit. I got a ton of questions about problem 2 here. Okay, the essence behind problem 2 is you've got a bowling ball rolling down an incline that's inclined at 30 degrees. Okay, so I know theta. As it rolls down, it experiences a force of friction. Okay, now the hard part about this problem is actually going to be solving for that force of friction, because they don't tell us a very crucial piece of information that usually makes solving for friction much simpler. They don't tell us what mu is. Now, if you guys recall, if we don't know what a variable is, or we're not given a variable, we cannot use it in our solution. So our solution cannot have mu in it at all. Okay? So I'm going to walk you through the steps about how to solve for the force of friction of an object rolling down an incline with friction, okay, where I cannot use mu in my answer. Okay? Start with, let's go ahead and draw the free body diagram. I've blown this up because I want to make sure we draw our force vectors in contact with where they are applied on the ball. Okay? So the first one is easy, right? We know that any object that is moving through our gravitational or Earth's gravitational field is subject to the force of gravity. And we know that that force of gravity always points horizontal or vertically, straight down. So I'm going to draw a force of gravity vector starting from the center of mass of my sphere here. All right, I can get this to work. There we go. And I'm going to draw it straight down. Okay, I'm going to label this guy mg is equal to F sub g, force of gravity. All right, notice I put it at the center of mass because the gravitational force always acts upon at the center of mass. Now, another thing we know is that any object that is sitting on a surface has a normal force, which is the force of that surface acting on the object. Now, that force acts at the application point, so that's going to be where the object touches the surface. So I'm going to draw a line. Remember, normal means perpendicular to the surface. So I'm going to draw a line like this, which is at a 90-degree angle to my surface, and I'm going to label it M. Okay? The last force that they tell us here is that the object experiences a force of friction. Now we know the force of friction opposes motion, so we know it's going to point up the incline. We also know that it is also applied at the point of touching between the surface and the object. So I'm going to draw a line like such here and label this one force of friction. Okay? Now, for part A of the problem, you're done. Okay? You don't need to do anything else. You've completely solved part A. However, I'm going to go one step further here, and I'm going to draw my components. Because if you recall from the dynamics unit, I've rotated my axes so that I have this as my new coordinate plane, where this is the x direction, and this is the y direction. Okay? With that being said, I know that I'm going to have components of the force of gravity. So let's go ahead and draw that triangle. All right, we draw this triangle down like this, a parallel line to the x-axis like so. We say this is theta. Now we know that theta is equal to that 30 degrees, okay? Because the interior angle of the incline is equal to this angle of this component here, okay? So using trigonometry, I can label these two components. This will be FGX, and that's going to be mg sine of theta. All right. Over here, I've got FGY, which is equal to mg cosine of theta. All right. So I've got a fully complete free body diagram for this situation, and now I'm ready to move on to part B, which is actually calculating the force of friction. Okay. So normally what we would do here to calculate the force of friction is we would use this identity that friction is equal to mu times the normal force. All right, which we know the normal force is equal to mg cosine theta, which would give us mu mg cosine theta. Okay? But notice that I have that mu in there, so I can't do that. Alright? I can't use mu in my answer. So, we're going to have to go through and solve a little system of equations. Okay? My first question to you guys would be here is what force is causing this object to rotate? And are any of the other forces actually causing it to rotate at all? Okay? If you guys recall, torque is equal to the force times the distance from the rotational axis, which is the center. Okay? So any force that acts on the center of mass, such as the force of gravity, applies no torque. Now we also know that if the force is perpendicular to the radial portion of your sphere here, then that's not going to apply a torque at all as well, which means the normal force here doesn't apply a torque either. Okay, normal force would just lift the object up, it wouldn't cause the object to rotate. So we know that the force of friction is the only force that causes this object to rotate. Okay, so the basic idea here is I'm going to use Newton's second law, which is the sum of the forces is equal to ma, and I'm going to use it in rotational, which says the sum of the torque is equal to I alpha. Okay, I'm going to use these two equations to solve this system and solve for the force of friction that causes the object to rotate. Okay, now what you're going to end up having to do here is you're going to want to start with the torque equation. Okay, torque equation makes it a little simpler, and you're going to get something where the force of friction is proportional to the mass times the acceleration, which you can then plug in to the sum of the forces to solve for friction in terms of just the given variables. Okay, it's easier to be explained by doing, so let's go ahead and begin. All right. First of all, they tell us that I of our sphere here is 2/5 m r squared. All right. We also know that alpha can be represented as a over r. So I'm going to want to do both of these things. I'm going to plug both of these in here. So that gives me that my sum of the torque is equal to 2/5 m r squared times a over r. All right. We can simplify that out a little bit further to say the sum of the torque is equal to, I'm going to cancel one of my r's, and I'm going to get this is 2/5 mr times the acceleration a. Okay, now we just discussed earlier that the only force that causes this object to rotate, or the only force that can apply a torque, or a non-zero torque, excuse me, is going to be the force of friction. Okay, so if we recall, torque is equal to force times the radius r. Okay, so let's go ahead and plug that in. Okay, we're going to have the sum of the torque is equal to the frictional force. Now the frictional force is applied at the outer part of the sphere, a distance equal to the radius of the sphere from the center. So I'm going to do this as F times the radius is equal to 2/5 m r a. Alright, now right off the bat here, guys, I'm going to kind of separate this so we can make it a little clearer. Right off the bat here, I see that I can cancel out my r's. So I'm going to cancel this r with this r, and that gives me that the force of friction is equal to 2/5 m a. Okay, now I have the force of friction is proportional to mass times acceleration. I think I can move on to my sum of the forces now. Okay, I may have to rearrange this later, but for now, let's label this 1, and let's move on to the second equation, sum of the forces. Okay, now the only place that this object is accelerating is going to be in the x direction. So I'm only going to be adding forces in the x direction. So we can state this a little more explicitly as the sum of the forces in the x direction is equal to ma. All right. Now, what is the sum of the forces in the x direction? Okay. Now I'm going to take going down to be positive and going up the incline to be negative. So the force of friction is negative. and the x component of gravity, which is this force here, mg sine theta, is going to be positive. Okay, so I've got ma is equal to mg sine of theta minus the frictional force. All right, now this equation is what I'm going to use to solve for the frictional force. But the next choice you have to make is, do I plug in 2/5 ma into this equation, or do I have to solve this for something else and plug it in? Okay. The answer to that question stems from the fact that I want to solve this equation for friction. So I don't want to plug in friction because I need that as my answer. But if you see here, you see that this ma is equal to mg sine theta. So if I treat ma as a variable, all right, excuse me there, guys. If I treat ma as a variable, I'm going to be able to plug in an ma from here. If I solve this for ma, plug it in there and solve for friction. So let's go ahead and do that over here, okay? I'm going to say this ma is equal to 5/2 the force of friction, okay? Now that I can plug in for ma and the sum of the forces over here, and now my equation is only in terms of friction, mass, the gravitational constant, and the angle, which are all given, okay? So let's plug in ma. So that gives me 5/2 force of friction is equal to mg sine of theta minus the force of friction. I'm going to group my like terms, so I'm going to add friction from this side, add friction from this side. If I take 5/2 and I add a whole, I'm going to get 5/2 plus 2/2, which gives me 7/2. So this becomes 7/2 force of friction is equal to mg sine of theta, which gives me the force of friction is equal to 2/7 mg sine of theta. Box this in, guys, accentuate it. That would be my answer. Check and make sure I don't have any unknowns here. I know the mass of my ball, I know the gravitational constant, and I know the angle theta. I'm all set. It would be my solution to the force of friction. Okay? Now, moving forward, guys, these processes and these steps will be very important. Okay? Anytime you are solving for force of friction on a rough surface where an object is rolling, you must follow this exact same procedure each and every time. Okay? For example, we're going to plug in. We have some of the torques here. We started here, then we went here. We used the sum of the torques to get an expression for friction in terms of ma. So we have something where friction is proportional to mass times acceleration and vice versa. So over here in this equation, I know that the sum of the forces are proportional to friction, and I can plug in my proportionality relationship for ma into this Newton's second law. I can simplify it like I did here and get a force of friction that is not dependent on the coefficient of friction. Okay, guys, I know this is a pretty complicated process. This would be a very helpful video for you guys to look back on as you work on more problems like this. I'll start coming up with a couple more I think that may be helpful for this. So if you have questions, please reach out. And hopefully this video was helpful, guys. Stay tuned for the next video where I'm hoping to combine the last two problems together here. All right. Thanks for listening, guys, and I'll see you soon.